Good morning, students. I am Dr. Sanjit Kumar, Assistant Professor in Physics, SD Jain College, Ara, under Veer Kunwar Singh University, Bihar, India. So today, as a professor of physics, I would like to tell you what actually happens in physics when we study. Actually, we start with unit and dimensions. Then we go to study the three equations of motions, which describes velocity, displacement, acceleration. That is how the system will evolve as the time goes on. We have three equations of motions. First one is v is equals to u plus at, where u is the initial velocity of the particle, v is the final velocity of the particle, a is the acceleration, t is the time. So the second one is s is equals to ut plus half at square, which is a parabola. The first one is a straight line, and the third one is v square is equals to u square plus 2s. Okay. So in all these three, what you assume that the acceleration of the particle is constant. As and when you assume that the acceleration of the particle is constant, you come up with these three equations of motion. Okay. With the acceleration, velocity, displacement, all these are vector quantities. And then you study graphically the evolution of the system, state of the system, evolution of the state of the system with time, acceleration, etc. Then comes the famous three Newton's laws. The first one is the law of inertia. It tells you what the force is. The second one is, it tells that the rate of change of linear momentum is equal to the force applied, external force applied. It tells how to get the value. The first one is a qualitative one. The second one is quantitative, measures force. Third one is, to every action there is an equal and opposite reaction, provided the systems are in contact. Right? So so all these three equations are very important as far as the laws of motions in macroscopic world and the motional particle in macroscopic world that we observe in day-to-day life. The two very important laws, which we call universal law, that is obeyed by all the particles of the universe. And the first one is the law of conservation of momentum, and the second one is the law of the conservation of energy. The first one is the law of conservation of momentum, which tells you that when the external force applied during a linear motion is zero, then a linear momentum is conserved. Whereas in rotational part, torque is the analog of force. When your torque is zero, then your angular momentum is conserved. Okay. So this is the first universal law. The second one is energy cannot be created, cannot be destroyed. Only it can be changed into one form to the another form. It cannot be destroyed. It cannot be created either. So the entire energy of the universe remains constant. And these two laws are the most fundamental, basic, and the building block of physics, of the entire natural phenomenon. Actually, with physics, we are studying nature. So these two laws are the real building blocks. And upon these two laws is dependent whatever be the interactions among the particles or whatever the behavior of anything in the universe is governed by these two laws. So keep in mind, these two laws are the basic. Right. So what we study in physics actually, or in anything, any subject, not only in physics, what you actually do, you observe something in the universe. Suppose you study physics, you observe something in this universe, and then you create a model. Okay, you describe it mathematically. You take the help of mathematics, and then you describe the model. Then you take the real problem of the world as a challenge and try to change some parameters in that particular real world problem, which you call simulation, and then tries to reach to that model that you have adopted to study. Okay, the best simulation is the one which will be more near to the model that you have adopted for the study. For example, the Carnot heat engine, what you study in thermodynamics, right? So what you study there, that the Carnot engine is 100% efficient engine. That means its efficiency is one, right? Now suppose based on this model, you design a motorcycle or an engine, electric engine, diesel engine, whatever that, and you try to make that engine more efficient and near to that Carnot engine. That's the real thing, by using lubricants or ball bearings, so that you may have minimum constraints like friction and other things. So you simulate, that is simulate, that kind of simulation, and bring it to the ideal Carnot engine. As soon as your engine is more and more efficient, it will come more near and near to that Carnot engine than the model you have used to study, either for a heat engine or for a refrigerator. Right? Two statements are there, Clausius, and the second one is the Kelvin Planck, that you know from second law of thermodynamics. Right? Now moving ahead. Now suppose you study light. Light is very important phenomenon in physics. And light, what you study, that light will have two peculiar behaviors. Two behaviors. One is wave behavior, another one is particle behavior. Now, depending on the experiment what you perform, light will actually behave as a particle as well as a wave. So first, we come to the wave part. There are three important phenomena. If the light obvious, that we will say that it has a wave character. The first one is the interference, right? So in interference you studied two very important phenomena, two very important experiments. The first one is the Young's double slit experiment. I think you remember, where from a source you create two virtual sources, right? And then you assume as if the light is coming from two virtual sources and they get interfere constructively and destructively. So from the central bright maxima, from the center to the even to the below, you get a patch of dark and bright fringes, depending upon the path difference or phase difference between the two interfering waves, right? Now this bright and dark fringes, these depends upon the path difference. If the path difference is an integral multiple of lambda, you will have bright fringe. But if the path difference is an odd half multiple of lambda, then you will have a dark fringe. But in terms of phase integral multiple 2 pi, you will have constructive. Odd multiple of 2 pi, you will have destructive interference, that is dark fringe. Here, actually, your entire wavefront is being divided into the two. So this phenomenon is known as the division of wavefront. When we're working with or when you're observing this Young's double slit experiment, the same division of wavefront you will observe when you will do Fresnel biprism experiment. Sure. Now there is a division of amplitude also. When you study Newton's ring experiment, that's a famous experiment, or Michelson interferometer experiments, where also you adjust the path length of the mirrors in Michelson interferometer, and you get what? You get interference fringes. You have two mirrors, one half silver plate, one is movable mirror, another one is static, and then from the movable mirror you adjust actually the path length, path difference, so that you can observe a set of fringes. There you have the phenomenon division of amplitude. Whereas in Newton's ring experiment, what you take, one planar convex lens is put on a glass plate, and then you shine sodium light, and then these lights, one will get reflected from the plane part of the convex mirror, and the other one will get reflected on this curved part, and then these two will get interfered, and from there you will have a patch of dark and bright fringes depending upon the conditions that I have already mentioned for path as well as phase differences. Here also you have division of amplitude. True. Now, apart from that, light has also particle behavior. For that, you have to come to the microworld. The famous black body concept given by Planck, he told that light consists of small quanta, small particles, of which has energy h times nu, where h is the Planck's constant, and each that quanta he termed photon. That's the bundles of particles of which the light is made of. That was the concept, and it got importance when Einstein proved and performed his famous photoelectric effect, and side by side by Compton, the famous Compton experiment that is studied, right? What happens in photoelectric effect? Just thank you. So in photoelectric effect, what you do, you shine a cathode with an ultraviolet light, and from there emission of electrons takes place. When it reaches the anode, when your circuit gets completed, you will have a deflection in the ammeter, rather galvanometer, right? Ammeter differs from galvanometer in the sense that ammeter only moves in one direction. It is unidirectional, whereas galvanometer is bidirectional. Okay. So I'm using word galvanometer in some sense that it will observe both the negative as well as positive currents. It directional. It gives the direction. Okay. Or otherwise, if you use ammeter, then you have to change the polarity. Okay. So what Einstein observed, that when we put external bias to 0, still we have current. When we shine light on the cathode, and intensity of the light depends, the maximum kinetic energy depends on the intensity of the light, right? Now, in photoelectric effect, what happens? Then when you light cathode with ultraviolet light, then you will have electrons, as I have told you. But when you put your external bias to zero, still you have current. And when you reverse the biasing, then also you will have current to a certain potential called stopping potential. Up to that level, you will have current. Above stopping potential, you have no current. So the energy that you have supplied to the cathode in the circuit is electronic charge times this stopping potential, and it will be equal to the kinetic energy, the maximum kinetic energy that the electron will have. So electron will have how much energy that we have to calculate. Suppose h nu is the amount of is the energy of the photon that incidents on the cathode. Then a part of that energy is being utilized by the material of the cathode, and that is the property of the any material of which the cathode is made. I mean, that energy is known as threshold energy. In order to take out the electron from its inner level to the vacuum level, right? That's on the surface. That is known as threshold energy. This is h times nu naught. We call nu naught is threshold frequency. So h nu energy we have given, out of which h nu naught is lost. So the energy left is h nu minus phi naught. Phi naught is the work function. And this is equals to E times the stopping potential, which is the maximum kinetic energy, right? So when you plot stopping potential, which is equals to h by h e times nu minus h by e times nu naught, phi naught by e. This is the equation of straight line having slope h by e, and its intercept is negative of the work function by e, that is negative on the y-axis below the horizon. And when you calculate that cut on the y-axis, you measure from the origin, you will get the work function. But the important consequence of this is that you can get the value of Planck's constant. If you measure the slope of this straight line will be del y by del x, that you can easily calculate. When you multiply this slope with E, the electronic charge, will have the Planck's constant. And from there, Einstein was able to calculate the Planck's constant. This value is very well known, 6.64 into 10 to minus 34 joule second, right? Joule second is the unit of accelerator as well, that we know. So this particle behavior was able to explain this photoelectric effect, right? And Einstein got Nobel Prize for this. He didn't get Nobel Prize for his general theory of relativity, which came in 1917. Right. So this is what is being observed in the micro world, right, which is a world of the order of Planck's constant. You can't observe this with your naked eyes. So this is a purely quantum mechanical phenomena. This is different from the classical physics that I have already told you, right? And these two wave and particle phenomena are interrelated in this micro world. That it, again, the meaning of micro world, I mean that the world which has an order of Planck's constant is 10 to minus 34 seconds, joule second. So 10 to minus 34, 35, you can't observe, my dear. That's why you can't observe it with your naked, but experiments confirm it. So any theory will be taken if it is being confirmed by the experiments. That's the law. I mean, that's the obvious way of taking a theory into consideration or study theory. If it is not taken by or any proved by any experiments, then obviously the theory will fail and it will not be taken. Right? So Einstein got the Nobel Prize for this. Right? And these particle and wave character of the light, these two are interrelated using the de Broglie relation, which is lambda equals to h by p, where p is the moment which which is very obvious, the particle behavior, and lambda is wavelength, very clear, the wave behavior of the matter. In H, here H, when H goes to 0, then according to Bohr's correspondence principle, your lambda and P are no more interrelated. So you are coming to the classical world. That's the famous Bohr's correspondence principle that you study. Clear? Right. Another one is very important phenomenon in physics that is known as the Heisenberg uncertainty principle. My dear, that's a very important law. Okay. What this uncertainty principle says, that position and its conjugate momentum cannot be determined simultaneously. Right? Position and its conjugate, that means delta x is the position, uncertainty in position, then delta px will be uncertainty in momentum. This is conjugate momentum, but not delta py. If you take delta x into delta py, then it will comes out to be 0. But when you take delta x into delta px, then this will be greater than or equal to h cut by 2. This is what the uncertainty principle says. Now I have read book by Sir Stephen Hawking. The famous book is The Brief History of Time, and I also recommend you to study, my dear students. Just go for it. You will really enjoy what the greatest mind of mathematics. He's a God-gifted mathematician, but he uses only 2 equations in the entire book. One is the uncertainty principle that I am explaining, and the second one is mass energy equivalence. E is equal to mc squared by this Einstein mass energy conversion equation. That the 2 equations he used. So I'm telling you that the uncertainty principle is of immense importance here, in the quantum world. Of course, in the quantum world, in the micro world. So what happens? That what is the consequence of this uncertainty principle? I'm giving you the flavor. One flavor I will tell you. Other flavors will come in my coming lectures. Okay, when I compare this classical with the quantum phenomena. Okay. One flavor I'm giving you. That the ground state energy of an electron, which always, according to Bohr, has got ground states energy equals to 0. Therefore, n is equals to 0, your energy is 0. Right? But, or even you study a very important phenomena like particle in a box, you will have 0 energy, ground state energy, a particle. But when you study a harmonic oscillator, you will find that no, the ground state energy of an oscillator is not 0. Right? So there, the energy is half h nu, or half h cut omega, which is known as the famous 0-point energy. Right? It means not only translational motion is involved, there the vibrational and rotational forces are also there, and therefore these uncertainty in position and momentum is rather a consequence of this. Is rather responsible for this 0-point energy, right? So this has got an immense importance when you study this quantum behavior, right? So students, this by telling all these things, what I mean that side by side, you just compare this classical and quantum world when you are studying both these two. In quantum physics, which is usually known as wave mechanics, also, you rather treat the particle as a wave. You talk in terms of probability, although you represent a wave, a particle or wave function, but its real interpretation comes out from its Born probability idea, according to which Well, uh, if the particle is somewhere in this space, then you calculate the probability of finding the particle in the entire space. It first comes out to be 1. But this is not with the plane wave, which the plane wave doesn't represent the real quantum picture. When you take the plane wave, what will be the probability? The probability will be infinite. It is not 1. So it will not represent the actual picture in quantum physics. You have to normalize that wave function. When you normalize it, then due to normalization procedure, when you calculate the probability, it will come out to be 1. Either you deal particle with box, particle in box, or you deal with harmonic oscillator or hydrogen atom problem, wherever you read. Everywhere you will come up with this, that when you calculate the probability, you will get 1. And the equation that describes the particle is the famous Schrodinger equation. Schrodinger is the real architect. I mean, when an operator operates on a wave function, you will get its eigenvalue, right? So operator is nothing but the inertia operator, which you call Hamiltonian. When it operates on operator, it gives its eigenvalue. Correct? We are going to celebrate this quantum era in 2025, which completes the 100 years of this year's Schrodinger picture, which was given in 1925, and this famous equation through which you study all this quantum phenomena. So, what I want to mention is that quantum picture is a truly, you can say, away from your visualization, but it is obeyed by all of us. It is valid in the micro world. To some extent, I would like to say in the macro world also. But the problem is the visualization. How you visualize it, your naked eyes cannot. That's why it's very difficult. I mean, I want to say that quantum physics is the fundamental one, and classical, statistical, whatever, these are the approximations. Classical is the approximation of quantum, I'd like to say. But the things are proved by the experiments. That's why to study. I mean it. But since you can't see in your eyes, with your eyes, only you can judge these phenomena, or whatever the theoretical ideas. These are the models. I already told you earlier that you have to adopt a model, and then you have to simulate it to the real world. So you have to adopt a model, and that model will be a mathematical version and theoretical concept when you take this theoretical study of this in quantum physics. And then you apply the laws of quantum mechanics. Well, especially this normalization or this probability concept is a natural outcome of the boundary conditions. Right? If you set a particle in motion or anywhere in quantum world, then what you do, its actual behavior will be like a plane wave that I have already told you, and it is a delocalized wave, and a delocalized wave cannot give any kind of information about the quantum particle. So to localize it from delocalize, you apply boundary conditions. When you apply the boundary conditions, then the probability of finding the particle within the space in which you are dealing it will be 1. The entire volume will be 1. So boundary conditions are of immense importance, my friend, my students. I'm telling you, just read boundary conditions, how it is going to be applied in systems and study when you're going to study this quantum behavior. I'm telling you, this is very important. So the nature of the wave function, what you it will be single valued, continuous derivable, right? And what its probability when you go to the infinite extent of this, when you put your r to infinity or so, it will goes to 0, right? Means asymptotically the wave function must vanish, right? So you have to check the behavior of wave function, how it behaves asymptotically, right? So with this, friends, with the emphasis to study, to give to rather ask you to study on boundary conditions, with this emphasis, and then in the next section of my video lecture, I will explain to you the behavior difference between your classical and quantum world, and along with that I will take one problem, quantum mechanics, and try to explain it to you in my next lecture. So thank you. I think this is enough dose for you. Now you go through it. So all the best wishes.